So good evening all. Vasevar sir, can I start?
You can. You can
Okay.
start, sir.
Okay. So just I have forwarded the 3 files to all the students. Okay.
Okay.
These 3 files are instruction and one Excel file, and one is actually kind of input reading to everybody. So just
Hmm.
today I will explain combined flow reactor in detail, how to do the experimentation and all in this virtual lab. And then maybe I will demonstrate how to use that Excel file. That is what we are going to do in today's this CRE class. Sir, I am audible clear, na? Audio is clear?
Yes, yes, sir. It is clear, very clear.
Okay, so just I will share my PPT, what I have at PPT. Mm. Please, you can see my PPT, na, sir?
Yes, it is
Uh,
okay.
any student? Jawal is there? Jawal?
Yes, sir, the PPT is visible.
So PPT is visible. My audio is visible. My audio is clear.
Yes, sir, it is clear as well.
So I will start this today. We are going to discuss this combined flow reactor. So what is there in combined flow reactor? The aim of this experiment is study of kinetics of reaction between sodium hydroxide and ethyl acetate in combined flow reactor. This is what aim of our experiment is there. This is first experiment in CRE lab. So basically in CRE lab, what we are going to do is we are going to have 8 experiments. So if possible, we will do physically also 8 experiment. If you come to VNIT personally during say last week of November or first week of December, if possible. If not, then if say situation does not improve and it is going bad because of this COVID-19, then we need to work with this virtual experiment itself. So virtually we have designed something for this combined flow reactor only. So this is what we are going to start. So we'll complete everything in this virtual experimentation CRE lab. So all 8 experiments, you need to complete the write-up in all aspects and submit before November. If you come personally in November, last week of November or first week of December, then you will be performing the experiment and submitting just a calculation and all, along with whatever report you are going to make now itself. Otherwise, you need to submit all these report of every experiment now itself using this virtual experimentation and all, and then and submit it. Submit. So you will be ready in all aspects, and you will be evaluated. If you are not coming to VNIT personally in last week of November, then your lab will be evaluated based on whatever experimentation you are doing virtually on only, and whatever be the assignments and everything. In this, we are going to have one lab test also, objective type. Once we have all these 8 experiments, so we will be having one lab test also, and then at the end we will distribute the mark accordingly, how much to all the experiments and everything. So today we will start with this combined flow reactor, study of kinetics of reaction. So this is ethyl acetate CH3. So CH3COO C2H5 ethyl acetate we are using, and we have sodium hydroxide. in all kinetics experiment we are using same reaction. It is giving sodium acetate CH3COONA and ethanol. So this is the reaction, and this is non-catalytic reaction. So if you mix just ethyl acetate and sodium hydroxide together, it will start reacting and it will give you sodium acetate and ethanol. So this reaction we are going to carry out in our all the kinetics experiment. So this is second order reaction. So 1 mole of ethyl acetate react with 1 mole of sodium hydroxide will give you 1 mole of sodium acetate and 1 mole of ethanol. And so second order reaction, so you can have this rate equation Ra equals to say K Ca into Cb, when Ca0 and Cb0 is not equals same, okay. If Ca equals to Cb, it can be written like Kca square. So we are doing all kinetic experiment for this reaction only, ethyl acetate and sodium hydroxide, and this is non-catalytic reaction. As soon as you mix ethyl acetate and sodium hydroxide, it will start reacting. So that is what we are using in all kinetic experiment, and we need to get the kinetic constant for this reaction, ethyl acetate and sodium hydroxide. So this is combined flow reactor. So it will look like this. So we have this rotameter A and rotameter B. So we can control the flow rate of fluid, say NaOH solution. This is NaOH solution, and this is the flow rate of ethyl acetate solution. So we can control the flow rate using this. So here both flow rate is going into mixing here and going into plug flow reactor first. So here this is going into plug flow reactor, and then it is going in CSTR. Then reaction will happen in this PFR and CSTR, and then sample will come here. So this is overall combined flow reactor, front view of combined flow reactor. Why it is called as a combined flow reactor? Because I have CSTR also and I have PFR also, and both are connected in series. First PFR and then CSTR, and hence it is called as a combined flow reactor. I have plug flow also, I have mixed flow also, both are there, hence it is called as a combined flow. So here some of the controllers are there. So this is on off button. So you can switch on the pump for NaOH. This is pump for NaOH. This is pump for ethyl acetate, and this will control the rotation speed of CSTR stirrer actually. And this is on off, main switch on, switch off button. So these are the some of the controllers in combined flow reactor. So this is the view of same combined flow reactor from backside. So this is say reactor, feed tank A, feed tank B. So this is connected to pump. This is the back view of same combined flow reactor. So this is connected to pump, and this pump outlet is going to a top tank. Okay, so overhead tank. This outlet is not going directly to rotameter. Similarly, here also there is an input to pump, and this outlet is going to a overhead tank. So this is not connected directly to rotameter. So this is connected to this overhead tank. This is the input coming from the pump and going in this overhead tank, and this overhead tank, and there are three output to this overhead tank. So this is the schematic given for this. This is the input coming from the pump. So input is coming in overhead tank, and this is overflow return to same tank. So there are two, ethyl acetate and NaOH. So this NaOH, whatever be the overflow means if level is above this, excess of NaOH will be flown back to a same NaOH tank. Similarly for ethyl acetate also, and this output is connected to rotameter, and this is for draining. So what is happening here, why this overhead tank is given, overhead supply tank is given along with pump? What will happen if I connect this centrifugal pump directly to rotameter and set the some flow rate? So this output of this centrifugal pump depends upon the heads given by this feed tank also. So as time progresses, because of this use of all this feed and everything, so what will happen? This head in an input tank is decreasing. Because of that, output will also decrease. Output pressure will also decrease, and it will give you fluctuating flow in rotameter. To avoid that, this overhead tank is given. Now what is happening? I am maintaining this head at this level. So whatever be the excess of fluid that is coming in here, it will be drained out. Okay, it will be not drained out, it will be returned back to the overhead tank. This is just for cleaning purpose, not drained out. This will be returning back to this. So what is happening? This head given to rotameter is constant always, so it will not change. So once you fix the rotameter flow rate to 5 lph, so it will not change because input head is constant, and be using the rotameter wall, you have fixed the flow rate to 5 lph, 10 lph, whatever flow rate you want. So it will not change. If I connect directly centrifugal pump, so initially when you set it to 10 lph, after some time you will see that it is reduced down to 9 lph, 8 lph, and so on. This is happening because the input head is changing. So to keep the head given to rotameter constant, this overhead tank is given. This is the main purpose of overhead tank, and this is what is happening. So both the input, so input from rotameter, so NaOH is coming in here, and ethyl acetate is also coming here. It is mixing here. Actually there is a single input after this, okay, single pipe. It is mixing and given to this rotameter. So, and this wall is kept initially open. Keep the wall open and wait for steady state. You start the flow rate. So experimental procedure says that.
हाँ प्रवीण. हाँ हाँ कंटिन्यू सर. सर कंटिन्यू. किसी का कॉल आया था.
हाँ 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 सर. So this keep all open. This is starting. You start the flow rate from both the rotameter. Say whatever flow rate you want, 5 lph, 7 lph, rotameter, NaOH rotameter, and ethyl acetate NaOH, ethyl acetate rotameter flow rate, and keep this wall open. So what will happen? Initially this fluid is coming in here, NaOH solution, ethyl acetate solution, mixed in here, and then it will be reacting in this plug flow reactor. So some reaction is happening in plug flow reactor. Then this output of plug flow reactor is given to CSTR, continuous stir timing reactor, and then some reaction will happen. Some reaction will happen in CSTR, and then you will get output from CSTR. So you need to wait for steady state. So how long you will wait for steady state is, you based on the volume of this PFR and CSTR, you will calculate the residence time. What is the residence time, total residence time for this PFR and CSTR? So you will wait at least 1.5 times 1.5 times the time equals to residence time. Say residence time is something around, say, 1000 second for both. So here say 700 second and here 300 second. Residence time for PFR is 700 second and this is say 300 second. So total residence time is 100 second. So you need to wait for at least 1500 second. Okay, say this is say 10 minutes, and say this is 10 minutes, 20 minutes is there, so you need to wait for at least 30 minutes to take the sample. So you will start the flow rate, keep this wall open, okay, keep this wall open, and wait for steady state. Wait for steady state. As steady state is achieved, then you will be collecting the sample from here. So this is the CSTR sample. Okay, this is CSTR sample which is collected from here. Then once you have collected this CSTR sample, then you will close this wall. So you will close this wall. So now what will happen? Fluid is coming in here, and just it will not go in CSTR because this wall is closed. So after collecting the sample, close the wall. This is the ball wall. Close this ball wall, and then what will happen? This is just output given at this point. So sample will start coming here actually. So you will collect the sample here, and this will be a PFR sample. So overall, what is overall process? You start the NaOH chloride, ethyl acetate chloride, keep the wall open, wait for steady state, then collect CSTR sample from here, and then close the wall. Once you close this wall, sample, this fluid will start coming from here, and you collect this PFR sample. Now you have two samples. One is a CSTR sample, one is a PFR sample. So here this is taken to be a input concentration. Okay, so this is Ca naught, Cb naught. Okay, Ca naught, Cb naught is given to this PFR, and here this will be the Ca1, Ca2 concentration of NaOH and ethyl acetate, and at this point you will have Ca1, Ca2 and Cb2. This is Ca1, Cb1. This is Ca2, Cb2. So pictorial representation. So same thing, if I represent pictorially, so I will have some solution. This is the solution filled in a tank, NaOH tank. Concentration of solution filled in NaOH tank. So C dash A0 moles per liter, and this is the flow rate of NaOH solution, liter per hour, LPH. Our flow rate is in LPH. Our rotameter has a unit for a flow rate, liter per hour. This is flow rate, and this is the concentration of ethyl acetate.
Sir, not audible, sir.
आवाज आ गया सर आपका? सर आवाज नहीं आ रहा है। सर आपका आवाज नहीं आ रहा है।
Now I am audible?
Yes, sir.
Yes, sir.
Okay. So where I was? On which slide? Jawab?
Sir, this slide only.
Okay. So now audible, na?
Sir.
Yes, sir.
So this everybody got this? Jawab?
Sir.
Yes,
Okay,
sir.
this is
From
clear?
pictorial representation. Yes, sir, from this
Yeah, yeah.
slide.
So this is what I was explaining. This is the pictorial representation of same combined flow reactor. So these inputs are given to you. So what are the input given to you? Concentration of NaOH in storage tank. This is concentration of ethyl acetate in storage tank. This is the flow rate of NaOH given to this plug flow reactor. This is the flow rate of given to plug flow reactor ethyl acetate. Both is mixed and given to plug flow reactor. So at this point, so I will have concentration Ca0 and Cb0, and then some reaction will happen in plug flow reactor here, and at output of plug flow reaction I will have concentration Ca1 and Ca2. So, and this output of plug flow reactor is given to CSTR, and it is this some reaction will happen here, and again this output of CSTR I will collect it from here. So I will collect two samples. One is at output from CSTR, one is at output from PFR. So if this is CA0 and CB0, this will be my CA1 and CB1, and this will be my CA2 and CB2. So you can see this is one sampling point. Okay, this is one sampling point. This is PFR sampling point, and this is CSTR sampling point. So which represent this point and this point. Okay, this point and this point is representation in experimentation. This is the PFR sampling point and this is the CSTR sampling point. So this data is given to you. So everybody will be performing the experiments with a different value of CA0 dash, CB0 dash, new A and new B, and there are I think 13 flow rate, 13 different readings are given. So you need to perform the experimentation using Excel file for 30 different readings. So now how to estimate this CA1 and CB1? So what is happening? This is non-catalytic reaction. So this is non-catalytic reaction. I have sodium hydroxide and I have ethyl acetate. Once I have collected the sample, here also I have sodium acetate and ethyl acetate and sodium hydroxide. Still reaction is going on in this sampling cylinder also. Okay, so as soon as collected the sample, you need to stop the reaction. So how to stop the reaction? So I can stop the reaction by consuming one of the reactant quickly. So that is what done in our CRE lab. So as soon as I collect the sample, I will consume this NaOH, remaining amount of NaOH, by using excess of HCl. So what I will do, I will take a 20 ml HCl, standard HCl. So excess of HCl used to consume unreacted NaOH and stop the reaction. So as soon as I collect the sample, I will mix with HCl. So I will have this 20 ml sample and 20 ml HCl. So I will make sure that concentration and volume of HCl in such a way that it is in excess. Okay, so it will not be deficient. So whatever be the remaining amount of NaOH which is not reacted after PFR and after CSTR, which will be consumed by HCl, and then I will get back this HCl by titrating with NaOH. So this is what overall process we are using to estimate the concentration of NaOH. So anyway, this you can estimate very easily. So this is pure NaOH. So you can titrate this with HCl and you can get this concentration. But as this is the mixture of ethyl acetate and NaOH, after sampling also the reaction is going on, as this is non-catalytic reaction. This reaction will not stop if it is coming out from PFR. The reaction is going on here, as this is non-catalytic reaction. Say zero point 0.1 normal NaOH, zero point 0.1 normal ethyl acetate, this reaction is still going on here. So to stop the reaction, to know the performance of this PFR, I need to stop the reaction. So I know input concentration. Input concentration can be estimated and it is given. So output concentration, as soon as the fluid is coming out from this PFR, so we need to stop the reaction. So how to stop the reaction? I will consume remaining amount of NaOH here. So whatever the remaining amount of NaOH is here, that will be, this sample is mixed with a HCl, excess of HCl, and remaining amount of NaOH is consumed here. And then I can titrate back and calculate what is the amount of HCl consumed by this NaOH, and I can calculate back the concentration of NaOH. Just I will explain this in detail again. So say this is, I have 20 ml standard HCl. So in all the experiment, this standard HCl means HCl is used of 0.1 normality. Okay, 20 ml is 20 ml standard HCl is taken in conical flask. So this is 0.1 normal HCl. Volume is taken 20 ml. So what is the initial number of moles of HCl? So this is the number of moles of HCl is normality of HCl or concentration of HCl. This is moles per liter multiplied by volume of HCl. Volume of HCl is in ml divided by 1000. 1000 is just this is moles per liter. This is moles per liter and this is ml. Because of this only this 1000 is coming. This concentration 0.1 normal means moles per liter and volume is in ml. Hence this is coming 1000. Okay, so this ml 1000 ml per liter. So this is the number of HCl present in this conical flask before adding the sample. Hello. So this is the number of HCl present in this conical flask before adding the sample. Then I will add the sample, 20 ml of sample. Say for example PFR. I have taken from PFR 20 ml sample and unreacted NaOH. So what will be unreacted NaOH? This is the concentration of NaOH multiplied by volume of sample taken from PFR, Vs, volume of sample taken from PFR. Again, this concentration is in moles per liter and this is volume is in ml. So this will be ml per liter. 1000 is nothing but the ml per liter, because this is in moles per liter and this is volume is in ml. So this is the number of remaining NaOH. Nr means this is remaining NaOH, number of remaining NaOH in my sample. Now I will mix this and this. Okay, this and this. So what will happen? This remaining NaOH will react with some of the molecules. This unreacted NaOH will consume some of the molecule from excess of HCl. So whatever be the HCl molecule, and remaining HCl is estimated by titration. Then this conical flask will add phenolphthalein indicator in this, and this will be titrating using standard NaOH. This NaOH is different. So we are using one NaOH which is given to you, that concentration is given to you in storage tank, that is input to reactor, and this is the standard NaOH. This is standard NaOH used for estimation of the concentration of HCl. So this 0.1 normal NaOH from burette and say end point is VPFR. So what will be the number of HCl remaining after reaction? That is nothing but concentration of NaOH multiplied by volume from PFR. So this is, say end point is VPFR. So this end point of this titration is PFR. So there, again, this is most.
Sir, you are not audible.
Sir, you are not audible.
सर आवाज नहीं आ रहा है, आवाज नहीं आ रहा, चेक करो सर।
Am I audible now?
Yes, sir.
So what is happening, man? This never happens.
अभी आ रहा है आवाज, अभी आ रहा है।
Okay. So where I was? This is clear
Sir.
to you, Jawad?
Yes, sir. Sir, the titration endpoint will be VPFR. That was the last point that discussed.
Okay. So this is titrated and this endpoint is VFPFR. So number of SCl present, number of molecules of SCl present here will be equal to number of NaOH reacted here. So that is nothing but this concentration of NaOH multiplied by volume of NaOH required in this titration. That will give me number of NaOH consumed here. That is nothing but remaining number of SCl present here. So what will happen, this minus this is initial number of moles of SCl present, and this is remaining number of SCl present, which will give me a SCl consumed by this sample. Okay, this is number of moles of HCl initially present minus number of moles of NaOH present, which will give me the HCl. Not this will give me this is initial number of moles of HCl minus this consumed by NaOH, or remaining NaOH will be give me remaining HCl. So rearranging this, I will get this Ca1. So this in Ca1, this is the volume of HCl. This is volume of HCl taken in conical flask. This is concentration of HCl, standard HCl taken in conical flask. This is concentration of NaOH filled in burette, and this is volume of endpoint of due date, endpoint of titration, PPFR, and this is the volume of sample taken from PFR. So this will give me CA1. This is concentration of NaOH after PFR. CA1 is nothing but the concentration of NaOH after PFR. So similarly, I can have for CSTR also. So only what is this volume of CSTR, again this endpoint is represented by VCSTR. So this will give me CA2. Okay, CA1 and CA2 is estimated. So CB1, CB0 and CA0 is given to you. So you can estimate CB2 and CA2, CB1 also. CB1 and CB2 can be estimated. So, and what is expected in theory of PFR? So you are expected to derive this equation. When CA0 is not equals to CB0, K tau CB0 minus CA0, that equals to ln CB0 minus CA0 divided by CA1 plus 1 minus ln CB0 minus CA0 divided by CA0 plus 1, and reduce this equation when CA0 is equals to CB0. This is when CA0 not equals to CB0. Now you need to derive the equation when CA0 equals to CB0 also. Now you can see, if you plot, so if you plot this term, okay, ln of CB0 minus CA0 CA1 plus 1 ln against tau. So against tau, if you plot this, what slope you will get? You will get the slope k into CB0 minus CA0, and this will be your y-intercept. Okay, this will be your y-intercept. So you need to draw the graph and get the value of rate constant. And using this also, only one unknown is there. So a CA1 is estimated using titration, CB0 is the initial concentration, CA0 is the initial concentration, tau is a residence time. Only one unknown is there, so you can estimate the rate constant also. Similarly, for CSTR, this is the performance equation for CSTR. So you need to derive this equation and reduce this equation for CA0 equals to CB0. Same thing for PFR as well as CSTR. Now the file is circulated to you. Okay, this file is circulated to you. So you can see there are four input given to you: CA0 dash, CB0 dash, new A and new B. This is the concentration of NaOH in storage tank. What is this? This is the concentration of NaOH in storage tank. Say for example, this is roll number BT18CME006. Okay, this is for roll number 18. Okay, BT18CME006. Serial number 8. Okay, this is 8th reading. So what he will be doing for 8th reading? So this is the concentration of NaOH taken in storage tank. This is the concentration of ethyl acetate taken in storage tank, and this is the flow rate of NaOH controlled by rotameter, and this is the flow rate of ethyl acetate controlled by rotameter. And then you will be getting an endpoint. So how to get the endpoint? I will just share another file. Can you see my screen now? Jawad? So this is the Excel file given to you. Okay? This is the Excel file given to you. Everybody got this Excel file? Anybody
Yes.
not got this Excel file? And this is the reading given to you actually. This is for roll number 1. There are 30 readings. This is roll number 2. There are 30 readings. So roll number 3, 4, 5, and 6. So for example, this 8th reading. So what it says, CA0 is 0.1, CB0 is 0.09. So what I will be doing, so you can see that this currently this reading is showing some odd values divided by 0 or something. So you don't do anything in this Excel file. You give the input here. So what is the input given on 8 number? It is 0.1 CA0, and then CB0 concentration of ethyl acetate is 0.09. So from where? From here, zero point 0.1 and 0.09. Then flow rate of NaOH is set. So what is the flow rate of NaOH is set? 10.1. 10.1. And then what is the flow rate of ethyl acetate set? It is 8.2. 8.2. Now you need to wait for steady state. Okay, this is volume of PFR, this is volume of CSTR. You get the residence time. Okay, so what will be total residence time? You need to wait at least 1.5 times a space time or residence time. So say if I wait 500 seconds, so it says 0. 0 indicates steady state is not achieved. So you may get wrong answer. So you need to wait for time greater than that. So if say this is say 900 second, now this is giving 1111, it indicates steady state is achieved. If you wait for 900 second, it is okay. Even if you wait for say 1500 second, it's fine. It doesn't matter. It should be greater than the time required for steady state. Once steady state is achieved, so you can see, so this is the concentration of NaOH. So this point 1 indicate the concentration of NaOH in the storage tank. This 0.09 indicate the concentration of ethyl acetate in storage tank, and this is the flow rate which you are setting. This is the flow rate set. This 10.1 you will be setting in this rotameter, and 8.2 you will be setting in this rotameter, and you wait for steady state. So what will be residence time? Can anybody tell me what will be residence time for this? Yeah, roll number 002, 18002. Who is he?
Hello, sir. Yes, sir.
002, na?
Yes, sir.
Yeah. So you got this flow rate?
Yes, sir.
10.1, 8.2, volume of PFR, volume of CSTR. So what
Yes,
will
sir.
be the space time, total space time for CSTR and PFR both together?
Was 1500.
1500. This is the space time. This is the waiting time actually. What will be
So
how?
divide by 1.5. 1500 divided by 1.5.
If say this is 5000, then
If waiting time is 5000,
what is space time?
sir, it will be 333 point 3000 something. 3333.
What is the definition of space time?
Sir, 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 it is, sir, the waiting time will be 1.5 times the space time.
What
So
is
we
the
will
definition of space
divide.
time or residence time?
The residence time will be the time required to reach steady state.
Residence time is the time required to reach the steady state. What is residence time and space time in CRE? Roll number 3. Who is roll number 3?
Uh, Hello,
Roll number 3. What is your name?
Sir Sachin.
Sachin. Yeah.
Hello.
Can you tell me residence time or space time?
Sir, it is the time spent by the fluid element to characterize the non-ideality in the reactor.
What? Can you repeat the thing?
अरे क्या क्या बोल रहा है यार क्या what is his name? Why is saying like this? It is not the distribution. Sir is asking about the what is the residence time.
Okay, sir. Sir, uh, I'm not sure.
Okay. Uh, Jawal, can you tell me?
Sir, residence time is the time spent by the component in the reactor.
Very good. So here, what will be the residence time? How to get this residence time? So I will get total flow rate. So this will be this plus this. So this is LPH. Okay. This is total flow rate, and this is CSTR. So residence time I will write CSTR. So that will be a, how to get this? So this divided by this, and this is hours. So this is hours. So this will be multiplied by, say, I want 3600. So this is the residence time for CSTR. So this is residence time for PFR. Residence time for PFR is again this flow rate, not this flow rate, this volume of PFR divided by this flow rate, and this is 3600 second per hour. So this is second and this is second. So this will be total residence time will be a this plus this. So you can see total residence time is 511 seconds. So if I wait for 500 seconds, so you can see steady state is not achieved. Okay. So because still my reactor is not filled at all. So 510, 520, just it is filled. So I need to wait at least 1.5 times this. 1.5 times this means at least I need to wait 750 seconds. Still it is not there. So 780, I think. Now you can see, if I wait for 780 seconds, then steady state is reached. Everybody got this? So initially you need to wait for steady state. Once you have set the flow rate 10.1 LPH here for NaOH and 8.2 LPH for this ethyl acetate, then you get the residence time and wait for at least this much time. Then only these readings are correct. Otherwise you will get wrong readings. Okay. So once residence time is reached, then what you will do? You will collect the sample from CSTR. Okay. You will collect the sample from CSTR first. Make sure that the ball wall between, so make sure that the ball wall between PFR and CSTR is open. This wall is open, and liquid is coming out from CSTR and collect the sample after this much time, 20 ml, and then close the ball valve. Then close the ball valve and then again collect the sample. This is the standard SCL taken. Where standard SCL taken? In this conical flask. Standard SCL taken, and this is the concentration of standard SCL, normal, moles per liter. And this is the concentration of standard NaOH which is taken in this burette. So with this input, this will be the endpoint. VPFR is the endpoint for PFR and VCSTR is the endpoint for CSTR. And this is the endpoint for which reading? For roll number 6, serial number 8. This is the endpoint. Likewise, you need to get all the endpoints. Okay, you need to get all the endpoints. Now here I will go to this instruction which is given to you. So these are the glasswares required. Precaution is given. General observation. This is the volume of PFR. Volume of CSTR is given. Experimental procedure is given. Everything is given, and then this is given to you. CA0, CB0, new A and new B. Now you estimate CA0, CB0. What is the tau? PFR, tau CSTR. Then VPFR, this is the burette endpoint for PFR, this is the burette endpoint for CSTR. Using this, you will be getting endpoint for all 30 points. So once you get for all these 30 points, this is your observation table. This is your observation table, and then you need to use this observation for calculation, and you need to complete the write-up with all these points: aim, apparatus, figure, theory. So what I am expecting in this experiment is typically derive the experiment, derive the equation which will give me a relation between rate constant and concentration. Rate constant and concentration, such that you need to prove a graphical plot of tau CA0 minus CB0 versus ln CB0 CA0 divided by CA1 plus 1 can be used to estimate the kinetic constant in PFR. Similarly, you need to prove that graphical plot between tau and CA0, CA1 minus CA2, CA2, CB2 can be used to estimate the concentration for kinetic constant for CSTR. Now, what are these CA0 and CB0? Is the initial concentration of NaOH and ethyl acetate. Okay. So, and initially this derived the equation for CA0 not equals to CB0. Similarly, CA1 and CB2 is the concentration of NaOH and ethyl acetate after PFR. CA2 and CB2 is the concentration of NaOH and ethyl acetate after CSTR, and derive this equation or reduce this equation, simplify this equation when CA0 equals to CB0. This is what expected to you are expected to write in theory. Okay, so glasswares required. You need to write all the glasswares required. You need to write all the precautions. You need to write all general observation, volume of reactor, experimental procedure, closing instruction, and calculation in following format. So you need to submit this table. So up to this, it will be just you can get this point from observation table. Then you need to estimate CA1. Okay, CA1, how you will get CA1? Endpoint of burette reading or PFR. That will give you CA1. CA2, this will be the burette reading using burette reading for CSTR sample. Now using this value CB0 and CA1, you estimate CB1. Okay, CB1. Then you can estimate CB2, and then you can estimate kinetic constant for PFR, kinetic constant for CSTR, and then plot the graph. Plot these two graphs and get the average value of kinetic constant, which is given by PFR and which is given by CSTR, and draw appropriate graph and report graphically estimated value of rate constant for both CSTR and PFR, and then you at the end you write a conclusion. So this is what you are expected to do in this experiment combined flow reactor, and your submission date is Monday. Next Monday by evening 5 o'clock you need to submit this write up for combined flow reactor. Jawal,
Yes, sir.
I'm audible to you?
Yes, sir. Yes, sir.
So you need to submit, and readings will be different for each and everybody. If I found that somebody is copying somebody else's calculation, and you need to give the calculation, sample calculation for 3 reading, at least 3 reading, okay, and you fix it. So serial number 5, 10 and 15. You need to give the sample calculation for these 3 readings. Serial number 5, 10 and 15. So sample calculation also, you this calculation table, okay. So you add one more point, sample calculation. So you need to give the sample calculation for 3 readings. Remaining you can fill it up and submit it. So I will be sharing with you a link. It will be exactly similar to what you have submitted the during your mid-sem exam. So you need to write. It should be handwritten. Everything should be handwritten. You write it properly. Draw neat and level diagram with pencils with all the nomenclature. So you can buy one book actually. So it should be like this. So everybody can see this. Can you see the book?
Yes, sir.
Jawad?
Yes. Yes, sir.
Yeah.
Yes, sir. You can
So
see.
it should be like this. This is practical book. Okay. And you need to send the PDF. You take a photo of experiment, say first experiment, combined flow reactor. Take a photo, merge into single PDF, and upload in a Google form. So I will be giving you the link for Google form. Maybe tomorrow or day after tomorrow I will give you a link, and that combined flow reactor should be submitted before Monday evening 5 o'clock. Clear? So anybody has any doubt in this? Now this is what I want to share about this CRE lab. So general instruction and these 3 files and how to use these 3 files. And so this most of the experimental procedure for this kinetics experiment for cascade CSTR and then isothermal CSTR, isothermal PFR, and this combined flow reactor is exactly similar. So you will find that it will be exactly similar, everything will be exactly similar. So using whatever information I have shared you today only, you can you can perform the virtual experiment for these 3 experiments: cascade CSTR, isothermal PFR, isothermal CSTR, and combined flow reactor. These 4 reactions are identically similar. Then we will be sharing with you similar documents for uh, batch reactor, semi-batch reactor also, and pack bed reactor. And then these are the 2 slightly different calculations will be there. And again 2 are totally different. These 6 are related to kinetics and 2 are related to RTD. So one is RTD study in CSTR, RTD study in PFR. These are the 8 experiments we are going to do. So 4 experiments are identically similar. So you can use this video. I'm recording this whatever with the presentation also I'll be sharing with you, and we'll be sharing with you a video for all the experiments also, so that you will have feel for these reactions.
Excuse
So
me,
yeah, tell me.
sir. We have to draw plots on graph paper or Excel.
Graph paper. It should be
Okay.
on graph paper. Okay. So this you buy this kind of book actually. This is practical book. So at the back side there will be graph. Okay. There will be graph. On this graph paper itself you can draw, and you can give the reference, or you can stick like this. Okay. Can you see
Okay.
this?
Yes, sir.
Okay, this graph paper is stick on this in between experimentation. You draw the graph and stick here. So, so this should be like this only, exactly similar to this. Okay. Anybody else? Any doubt? Vaseva sir? Piyush sir?
हाँ सर बोलिए.
You want to add something, sir?
नहीं नहीं ठीक है ना, इट्स ओके दैट. बट who will take the next, means every Tuesday we have to take the this
No. We will
or
complete as early as possible, sir. Not every
okay.
Tuesday. So maybe in this
Okay.
week I will complete all these 4 experiment kinetics,
Okay,
and
4
then
experiment you will go.
so because we need to complete everything before November last week.
Before November now. Okay, no issue for
So
that.
all submission and everything. So we'll complete 8 experiments as early as possible. After 8 experiments, we'll have one test, online test for CRE lab. So
Yes.
at least we'll be ready with evaluation based on this
Okay.
virtual experimentation. If the student comes to VNIT personally, then they will be just performing the experiments and just
Yes.
they can submit the observation table and sample calculation. That's all. That is there they will end. If they are not coming, then this using this virtual lab and their submission only we will be evaluating CRE lab.
Okay. Okay. No issue. Mine is also ready. Once you finish, then I will start for that RTD. No problem.
Okay, sir. Okay. Piyush sir, you want to add something? Piyush sir?
Hello.
Sir. You want to add something?
Sir, this titration thing we don't need to mention for every experiment, no? That initially you said,
Not needed.
yeah.
Not needed.
So,
Not needed.
like if I start with semi-batch reactor, so directly I can start explaining
Yeah.
the yes. Okay.
So for all the students, this overhead tank is common to all the experiments, and this titration is also common to all the experiments.
Yes.
So hereafter we will not be mentioning this again and again. Same thing. So why this overhead tank is used? To keep a head given to rotameter constant. That is the main purpose of overhead tank. And this why this titration and excess of HCl is used, so we can consume the NaOH quickly and then we can titrate it back remaining HCl. To stop the
वही बोल रहा था
reaction
अभी
we need to
ट्रिगर लेना
consume.
बुरा रहा है.
So
थोड़ा
that
सा
is what.
ज्यादा डाल के एक बार का ले लो.
So anybody has any doubt? Yeah, roll number 87, BT 18, roll number 87.
Sir, how to calculate CA1, sir?
CA1 I have shown na.
Sir, but we will not do titration virtually, no, sir. Then how to calculate CA1?
So you have endpoint na.
Point.
This is what I have explained na. Can you see on my PPT? CA1.
Yes, sir.
What is this NHCl?
Sir, normality of standard HCl used.
Okay. What is VSCl?
20 ml, sir.
Okay. What is NaOH?
It is NaOH, standard NaOH normality 0.1, sir.
Okay. What is VPFR?
EPFR, sir, that burette reading.
Yeah, burette reading. From where you are getting this burette reading?
Sir, now in virtual, how can we get, sir, burette reading?
This is what this Excel file is given to you, na?
Yes, sir.
Yeah, this will give you VPFR. Look,
Sir,
if I change concentration na here, instead of say 0.1, if I say 0.01, now you will see that this burette reading is changed.
okay, we should use Excel sheet for generating the burette reading, sir.
Yeah. Say instead
Okay,
of
sir.
say I will be using 0.15. So you can see what is the burette reading now.
Yes, sir.
So,
Yes, sir. Understood, sir.
what we have done, we have tried to have virtual experimentation. Now you are doing exactly experimentation only. Instead of in lab, here you will be setting. So what you will be setting? The concentration of NaOH, the concentration of this thing, and then volume of volumetric flow rate for NaOH, volumetric flow rate for this thing. Even you can change these also. It will change accordingly. If you take say 10 ml sample only, again you will see that this burette reading are changing. Okay,
Okay, sir.
so so this Excel file is designed in such a way that it will give you feel of virtual experimentation. And here by side everything is mentioned. What is step one? You read it here. Okay. Prepare the different concentration of NaOH and ethyl acetate. Range of NaOH you need to take. Range of ethyl acetate you need to take. And what is your this how to select this? This you need to. What is your roll number?
Sir,
What is your
23, sir.
23? So I will go to 23, roll number 23. So this is 22. So you need to do this for this. Okay. This is your input reading. So what is your serial number one? CA0 is 0.13. So I will be using this 0.13, 0.13. Okay. CP0. CP0 is 0.07. 0.07. And then flow rate of this thing is 13.8 and 6. 13.8 and this is 6. Flow rate of ethyl acetate. So you can see steady state is achieved. Okay. So you can
Yes,
go
sir.
ahead and this will be your endpoint actually. You can see this will be your endpoint. 5.1 for PFR sample, 5.9 for CSTR sample. Now
Okay,
you
sir. Okay, sir.
using this formula you can get CA1.
CA1, yes, sir.
You get CA2.
Yes, sir. Thank you, sir.
Okay. Now once you have CA1 and CA2, you need to derive the equation actually. Okay. This equation you need to derive. If you have CA1, so you can get the kinetic constant corresponding to PFR. If you have CA1 and CU2, you will get a kinetic constant for CSTR. So using this, you need to fill the table actually. Okay. So this instruction, you read this instruction properly. Here, everything is given actually. Fill in the appropriate value in a box, color yellow in Excel file, endpoints at the bottom of the sheet in same Excel file can be used for calculations. Okay, it is given actually. You read the instruction properly and then you go ahead. So where is roll number 18? 87. 87 I asked, na? 87 is sleeping or what?
No, no, sir.
Huh? Okay. What is your name?
Puneet Jain.
Puneet Jain. So got the point?
Yes, sir. Yes, sir.
Okay. So can you explain me briefly?
Sorry, sir, unable to explain at this moment of time.
Okay, okay. So, any doubt in this? Anybody
Sir,
else?
while we are
One by one, one by one. Yeah, tell me. Ankit, roll number 26.
yes, sir, while we are stating the apparatus for the experiment,
Uh-huh.
so do we need to state the apparatus that we have seen in the slides, or something else like we know for from the titration or something like that?
So it is already given this, use this instruction file and a photographs shown to you in
Okay, sir.
this thing. Use both thing and combinedly you can write. So
Okay, sir.
actually main aim of all these exercises, you should get familiar with this how to estimate the kinetics in CSTR and PFR. Ultimately in industry, whenever you go to industry, actually you will not be finding the kinetic constant will be given, so you should be able to get the output concentration. So here you can estimate the output concentration and get the kinetic constant. So that is what means. So you should have feel. If you could have been here personally in VNIT, so you could have performed the experiment and get the readings actually. So as you are not here, so we have just got this Excel file, and using Excel file you can get the end point and do the calculations.
Okay, sir.
So anybody else?
Hello, sir.
Yeah, Jawan.
Hello, am I audible?
Yeah, tell me.
It was not me, sir.
So
Sir,
who is
we
it?
in titration. Sir, I'm roll number 25. In
25.
that titration,
Uh-huh.
why means when we titrate again with NaOH, then the remaining ethyl acetate will also react. No, sir?
No. What is happening? That is very good point actually. Good question. So now, where it is? Yeah. Now here, what is happening now? Here I have HCl. Okay, remaining HCl. Can you see this slide?
Yes, sir.
So here, what are the components I have? Remaining HCl and remaining ethyl acetate. Okay. Now when I am adding this NaOH, both will compete for reaction with NaOH, HCl as well as ethyl acetate. And if you see this acid-base titration, this is very fast reaction. NaOH and ethyl acetate, the kinetic constant is almost infinity. So this is infinitely fast reaction, NaOH and HCl. As soon as you drop this NaOH, it will react with HCl only. It will there is a competition there, as you told, there is a competition between ethyl acetate and HCl, but HCl has highest affinity towards NaOH because this is very basic acid base concentration, and HCl is a strongly acidic and NaOH is a strongly basic. This acid base reaction titration is very fast reaction, instantaneous reaction. So whatever NaOH you are adding initially, it will be consumed by initially HCl only, and this will happen. The endpoint will, you will not get very clear endpoint, because what will happen? NaOH, extra drop of NaOH, you will, that color of the phenolphthalein indicator will change. But if you wait for 5 to 10 minutes, then again it will disappear. Now thereafter, what is happening? This extra NaOH will be consumed by ethyl acetate. Okay, got the point?
Yes, sir. But in means such experiments, such titrations we did in earlier also in organic chemistry. So during such titrations we use methyl orange, sir. Means we
Yeah,
need that endpoint in which HCl is consumed and the ethyl acetate is remaining.
yeah.
Because the phenolphthalein will give endpoint at pH almost 10, and at that pH, ethyl acetate will also be reacted.
Okay, methyl orange. I don't remember actually. Maybe methyl orange only. We will use methyl orange. It doesn't depend upon this phenolphthalein indicator, na? Indicator how it matters.
एक्सक्यूज मी सर, सर मैं थोड़ा मैं एग्जिट हो जाऊं सर, हो गया?
Okay, okay, sir. Okay, okay.
हाँ
Okay, sir.
मुझे थोड़ा सा जाना था, हाँ ठीक है
Okay,
ना,
okay.
ओके सर, थैंक
Okay. Yeah, we'll use methyl orange as an indicator. Actually. No problem.
Okay, sir.
Anybody else? So submission date is clear to all. It is next Monday, 19th, 5 p.m. and it should be submitted through a Google form only, no mail. And I will be sharing the link with Jawal. Okay, Jawal, or in this class group also, I will be sharing the link. On this link only, you write it handwritten, all the points. What are all the points? This write-up I want: aim, apparatus, figure, theory, then glasswares, precaution, general observation, volume of the reactor, experimental procedure, closing instruction, calculation in table format, and sample calculation for serial number 5, 10, and 15. And then conclusion, then graph and conclusion. So concluding remark based on observation. What is your concluding remark? This is what I want in write up. Okay.
Yes, sir.
So what, Javal, what are the other labs you have in this semester?
Sir, heat transfer lab is there.
Okay. Now say for remaining 3-4 experiments, kinetics experiment, it is exactly similar thing. I will share the similar Excel file with you. Is it okay, or I need to take the class for that remaining experimentation also? Jawal?
Sir, we can go through the PDFs and then have a doubt session if someone has any doubts in it. That would be better because if it's similar,
Okay,
then
okay, okay. So I will make uh, uh, files ready for all remaining three experiment, and all together we will have some doubt clearing session like this only. So you go and whatever currently we are taking class, this also I will try to get the video and upload somewhere, or pass it on to you somehow. Okay. So this video is there, and we have a video for all experiments also in our CRE lab. CRE lab, all 8 experiments videos are ready. That will also I will pass on to you, and you just communicate with everybody and using video, these three files, and whatever with the current instruction given, and whatever with the demonstration given now, actually demonstrated in these online classes and everything. Using all this, you need to have this virtual lab for CRE actually. So maybe so if somebody knows Aspen and HYSYS, it will be very easier actually. There also you can use this CRE lab fundamentals and everything. But this is exactly what we can have currently. Everybody can handle that Excel file and everything, and then you can get the values. So is it okay for everybody? Anybody else has any doubt? Pawan is there? Pawan Edward? Okay then, Java. It's fine now?
yes, it is fine.
Okay then. So I will call up this class, and we'll see you in next class.
Thank you, sir.
Okay, thank you.